Welcome back, everybody. How was homework 1? Okay. Manageable? They get exponentially harder, so you want to start out with something reasonable. I'm kidding. All right, so homework 2 is up, and it's due a week from right now. I'll have office hours next week, probably Wednesday, but it'll either be in the morning or the afternoon. I'll tweet about that to let you know. Those of you who came to office hours yesterday, it seemed to be super helpful. So if you aren't able to make it, maybe you could find somebody in the class who's going to plan to go and connect with them Wednesday later in the day or something. That would be a good idea. Okay, so I tweeted a, I tweeted a visualization of this logistic map that I think is kind of nice. So this is something you can go play around with, and it's a little smoother than the MATLAB visualization that we've been using and that you can use on your homework. It's done by this guy, Dirk Brockman, who's done some really interesting research looking at how people move around on the Earth. He studies things like epidemics, and initially, one of the great ways to study mobility, human mobility, was to look at actually dollar bills. So he had this website, Where's George, where people could type in the serial number of their dollar bills, and when a few people had done it, you could see the distance it had traveled, and pretty cool. Where'sGeorge.com. So anyway, this website, the visualization has a slider here for the parameter values, so you can see what the logistic map function looks like, and then there's a few orbits starting with different initial values, not close to each other. You get to see what they do. So you see a bifurcation here from, there's a sink, and then all of a sudden that period 1 sink becomes a source. So now there's a period 2 sink, and I guess I can turn off the transient stuff as well, so you can see just what the attracting state looks like, which is kind of boring for the period 1 sink. But you get the square in the cobweb for a period 2 sink, and then that square sits around for a while. But eventually, F composed with itself, the slopes of those intersections corresponding to that orbit, those slopes go above 1 in magnitude. And when that happens, they're both becoming negative and equal. Slopes are, first initially they're positive, and then they become 0, and now they're negative, the slopes of the second iterative of the function. When they go below -1, the new sink is a period 4 orbit. And that period 2 sink or that period 2 orbit is still there. It's just you wouldn't realize it with initialized, with these 2 initial conditions. You would never see it because they don't get iterated to land on that period 2 source. And unless you land on that period 2 source, you're going to be pushed away. Remember the definition of our source 1, the fixed point source, the definition was put a little interval around it of size epsilon, everything leaves except the source. It can't leave. Questions about things I've said so far? I do think you should play around with this. I think it would help you. You can turn on higher iterates, F3 and F4 of this function, and have a look at what they look like. I'll do that here in a second too. But questions about what we've seen? Yeah.
So when we're talking about sources and an increasing number of sources,
yeah.
On a computer you'd never actually land on it.
No, that's a good question. So for example, the fixed point at the origin is a source. And the question is well, how would you ever see them on a computer? Well, if I put 1 in as an initial condition, it maps to 0 and then stays put.
So 0 is, are the others landable?
Right. Usually not. Typically not. And one of the reasons why is, so let's say that square that we know is still here, right? If we have F2, we know that there's a square that one end is on that point and the other end is up here and where the light blue curve crosses. Right here. So there's a square in there that's a period 2 source. And we saw it a minute ago as a stable, it was a stable period 2 orbit. If I slide back here, there. So there it is. It's attracting all the points between 0 and 1, except for the fixed point right here, and the fixed point right here. So all of the initial values between 0 and 1 go to this square. And later in the semester, there'll be theorems that we can write down that prove that that's true. Because right now, you kind of are still learning what's going on, and you're just kind of taking my word on all the initial conditions do that, except for the fixed points. Okay, and then when that period 2 orbit becomes unstable because the slopes of the light blue curves get steeper than -1, it's pushing things away. And you can ask the question, well, like on the computer, would we ever actually initialize it? And with a random initial condition, no. If I chose this initial value here, and I could represent it exactly in the computer, that's a key piece of the sentence. Because if I don't represent it exactly in the computer, because in base 2, 52 bits, it's got more stuff after those, more bits required to represent it, then the problem there is that I'm not on that source. And so unless when doing this calculation where I multiply it by 3.468 and then multiply that by 1 minus this value, unless that happens to all the arithmetic happens, all those errors happen to cancel out, very unlikely, and land me on the other one, I'm going to land near the other one, and I will be pushed away exponentially from that period 2 source towards this period 4 sink. Yeah, so most of the time in these images that we're going to see, we're only going to see the long-term attracting behavior. Here I've turned off the transient, so you don't see all the cobwebs that lead to this period 4 sink. But people, so my advisor at Bates College when I was an undergrad, his name was Chip Ross, and he makes these beautiful bifurcation diagrams like the ones that we've looked at for the logistic map, like this picture here, but has a way of computing what those sources look like. And if they were on this picture, for example, this fixed point would still be here, right? And so we actually know analytically what that value is because we can just solve for what the fixed point is as a function of the parameter. For example, when the parameter is 4, that value is 3/4. You figured that out on your homework. And so there is a, we could color it instead of black, we could color it red or something like that. There's a source that continues through here. And similarly, that square that we were just talking about, it's a pair of red lines that go here and here that you never observe on the computer, but they're also there. And that continues all the way through. I don't know if I answered your question, but yeah, most on the computer, very rare that you actually land on a source.
Or probably in the real world, even less.
Totally, yes, yeah. And in the real world, most of the equilibria that we observe, they're attracting, but it's hard to tell if they're going to stick around because the parameter's wiggling too, because we're changing the system. Yeah.
So presumably you couldn't land on that source because it's an irrational number, and the digits go on forever. But with rational numbers, can you find those?
Good question. Yes, great question. So if the value of that fixed point is a irrational number, when we put it on the computer and truncate, at the 52nd bit, then we're not at that fixed point and we will go to whatever the sink is.
Right.
If it's a rational number, it can still not fit in those 52 bits. Yeah, like for example, on the computer, 1/10, if I write that in binary. I can't remember what it is. It's something like 0.00110, where the 0110 is repeating forever.
Right.
That's rational. Anytime you get in binary or base 10 or any base, a bar over some digits that are going to repeat indefinitely. That's a ratio of integers, 1/10. But if you truncate it at the 52nd bit, you're not quite at 1/10. You're at 1/10 minus plus or minus 10 to the minus 16. You're close. Plus or minus 2 to the minus 52. Yeah, so you're close, but you're not on that spot. So even rational value fixed points that are sources we won't be able to land on them on the computer. Yeah. Yes? Yes, yes. So with infinite precision or variable precision arithmetic, adjustable, you can choose how many bits to keep. Or clever ways of using fractions to do arithmetic instead of this base, which software can do. Then yes, you could represent a rational number, but it's symbolic. You're doing it symbolically. You're not putting all those bits on your machine. Yeah. Other questions? All right. So this app here, I think, would do a nice job of letting you kind of test your intuition about some things and answer questions you're going to have over the next couple weeks on your homework about what happens with higher and higher iterates. So what I was saying before is as we go through this period doubling bifurcation sequence where we go from fixed point sync to period 2 sync over to period 4 sync, is we should see if I put the let's see, roots of f4, that's what I want to look at. Okay, here's f4, wiggly out at the edges. Polynomials get wigglier and wigglier as you make them higher and higher orders. F4, it's got, right now, it's got 4 points of intersection, and in fact, it shares those all with F2, which is why there's no period 4 sync here for points to go to. But as I dial this parameter, what's going to happen here? Let's see. Well, it starts to wiggle some more. F4, F is a degree 2. It's a quadratic. So I compose it with itself 4 times. That's a degree 16 polynomial. So this is kind of a boring looking degree 16, the light blue now. But as I keep increasing this parameter value, it's going to want to wiggle more. And so when it starts to do so, the spots that it agrees with F2 they're no longer the only places that it crosses y equals x. And so here we'll see that not only does the slope of the crossings at this square go above 1 in magnitude for F2, it also results in F4 having these intersection points, which you can't really see. Let me make it, I can spread them out a little more before craziness happens. Okay. So here, so F2, this F4 has, let's count the intersections. It's got 1, 2, 3, 4, 5, 6 intersections with y equals x, F4. 2 of them are intersections that had from the original F, fixed points. Did I not count enough? Right. Yeah, I think if I plot F2 on there, it'll agree at that spot. And where's the other one? Oh, I just can't see it. It's up there. Yeah, very good. So there's an intersection there that I missed, and there's another one up there just between the 2 that I missed. So there are 8. Good. And so these 4 intersections that are sitting on the sort of nested square, that's the period 4 sync. And in a second, as I dial this parameter, this slope here, and by the way, the slopes at all 4 of these places should be the same. You were working on that on your homework, yeah? So the light blue, same slope at all 4 spots. And as I dial it a little more, and this period 4 sync becomes unstable, their slopes will become bigger than 1 in magnitude at those intersections. Cool. And then we'll see, we're not iterating, by the way, F4 in the picture. We're iterating the original F. Cool. So now we have these sort of double nested squares. This is a period 8 sync. And the period 4 source is still there. We just don't see it. Questions? This is pretty cool. Any questions about it? All right. If I click on F3, am I going to have any agreement between F3's intersections and F4's intersections? Anywhere? Yeah, at the 2 fixed points, I'll see some agreement, right? And in fact, if I can wander my way towards, let's see. Let's see if I can wander my way towards, what's going on here? This is F3. So it's a degree 8 polynomial, and it's not wiggling so much yet. Something's going to happen. Let's see. So bifurcations, period doubling bifurcations, somewhere around 3.8. Remember we had a weird little window happen? It's hard to even see what's going on. This is the attractor, by the way. So the transient stuff's not on there. Turn it on, turn it off. It's gone. So the attracting state, the one where you run it for a long time and then start looking at what's going on, that's what it looks like. It's not just the square anymore. There's lots of stuff. Cool. And then I said around 3.82. Oh, something cool happened. So yeah, you could see if I go dial back a little bit, this is that set of pictures, the suite of pictures in your homework that are static, where you see this. Maybe I could just turn them all off so we can watch what happens. So the polynomial is wiggling. Now this is degree 8. It's going to come and touch the line y equals x at all 3 places at the exact same moment. And that's where the chaotic stuff disappears, and we collapse down to this period 3 sync. And in fact, there are going to be 2 of them. Yeah? How many period 3 orbits am I going to have? 1, 2, 3, 4, 5, 6, 7, 8. What's going on there? Which period 3 thing do I go to? Are they both sinks? Are they both sources? What do you think? What's going on? I have how many intersections with y equals x? Let's count them. I did. How many are there? 8. Okay. 2 of them are fixed point sources from G. If I turn on the attractor, oh, dial me back. There. I turned on the attractor, and it looks like there's, just one of those period 3 orbits is what ends up happening. What about the other one? What do the slopes look like for the other one? They're all bigger than 1, which means that as a fixed point of F3, each of them is a source. As a period 3 orbit point of F, they exist, but we would never find them because they are also a source. So everything that's not on that, that little shape will go to this. Wow, there's a lot of things happening. What do we think of this picture? You feel like you understand? So one period 3 orbit that's a source, one that's a sink. In your periodic table of doom you were filling out, which you're going to do more than once for other functions other than just the logistic map. I didn't ask you to tell me about the stability of those things, but as you might imagine, it is going to be interesting if there's more than one sink, right? The first example we looked at in class I can't remember if it was the first or second day, we had this cubic that we were looking at and trying to decide, what's the deal here? What about the basins of attraction of these 2 sinks? They were really interesting, and they were bounded by points that eventually landed on the source at 0. Those points that forward mapped to 0 were the boundaries of the basins of attraction of these sinks that were bounded ultimately by the period 2 orbit plus or minus root 5. This is so cool. I'm so happy to talk about this with you. All right. So, yeah, that kind of came out of nowhere, right? So the long-term attracting behavior was after this period doubling cascade, we had this sort of chaotic stuff, and then there are these windows, period 3 window around 3.8. There's a period doubling bifurcation here, and I don't know if I can drag this carefully enough, but okay, there's an example. Period 3 went to period 6. And the green curve would do the same thing. It would ultimately end up doing the same thing. And this period 6 orbit would go to period 12. Cool. Questions?
Are the properties repeated? So we have basically went back to a period 3 orbit. We had a period 3 orbit prior, and then all this stuff happened after that.
We never had a period 3 orbit in the beginning.
Oh, we didn't?
Yeah, we didn't. So if we think about what F3 looks like, let's look at just F3, and we go wandering back. We have the places that F3 crosses y equals x are the same places that the original function f does for a long time. The period doubling bifurcation route to chaos happens. Still don't have any intersections with F3 and y equals x, which means no period 3 orbits. Yeah? And so it's tricky. It's like, oh, well, we got every power of 2, but no powers of, no 3 or doublings of 3. And then, the period 3 happens when all 3 of these, these 3, 1, 2, and 3, those local maxes and mins come in touch, and then they push through, and one of them's a sink, one's a source. But that's the first time we get period 3. Period 3 ends up being super important, and we're going to talk a lot about it. It's maybe not easy to see right now why that is, but the concept actually so I mentioned on the first day that this guy Lorenz wrote this paper, Deterministic Non-Periodic Flow, in this Journal of Atmospheric Sciences in 1963. It was largely ignored by the scientific community because it was a weather prediction journal. And then 10 years later, my advisor at Maryland, Jim York, wrote this paper called Period 3 Implies Chaos, and rebranded this concept a bit. And so that word stuck around. It's shorter. And And then, so he wrote this paper 10 years later, period 3 implies chaos, which is on the website for the class. You can look it up. It's pretty dense math. But we'll absolutely understand the reason why in a few short sentences later in the semester. There's some really nice theorems about it. But period 3 will become important. But this, this appearance of it is the first time it happens. It doesn't happen during that cascade doubling. Yeah. Other questions? Okay. Very good. So, other things to say. So we got to define some words. They're going to get us through. I should say, the plan, by the way, is homework 2 is up, and it'll be more investigations of this one-dimensional map stuff. But starting next week, we're going to leave the one dimension and go to higher dimensions of this sort of behavior. And we'll be sort of talking about the three-body problem in astronomy, trying to map, the orbital mechanics of bodies as they move around each other, which is one of the reasons one of the reasons why people were thinking about this originally 100 years ago. Just didn't have computers back then to see what the solutions to those problems looked like, and they're really interesting. Okay, but we're going to do some definitions here. One is this concept of sensitive dependence. On initial conditions. Which is a lot to write, so I'll usually say SDIC. And the idea behind this sensitive dependence on initial conditions, we've sort of danced around it a bit, but I think we can get a feel for it here. So if I set the parameter, of one of these simulations to 4, and I start with 2 initial conditions, one that's 0.01 and one that's 0.01, but I'm going to do my arithmetic in double precision. The computer, by the way, would iterate this 1 billion times and blink just as quickly. It's really simple what we're doing here. But I'm just iterating it a few because it kind of shows me what's going on. All right, so we're just in, what AltMATLAB's doing is deciding, am I going to keep, basically 8 digits or 16 digits in base 10? And so we're starting with 0.01 in both cases, and for a while they're close, like the first. So for the first 2, they're the same, but the third iterate, one of the maybe the last bit in the single precision calculation is different. Okay, so what happens then is the 2 initial conditions are not, the 2 states are not at the same place, and once they aren't, parameter value is 4, by the way, remember, and cool things about G when the parameter is 4. There's a periodic source of every period. They're all pushing each other away. 0.01 is not on one of those periodic sources. So the stretching that's going to happen when points get pushed away from a source, that's happening everywhere in the interval, including around this point. It's getting, things are being pushed away from it. Basically, every point is acting like a source. Almost every point is acting like a source in this interval. So, what do I want to say? Okay, so by iterate, 13, 14, 15, where am I? It's doing okay for a while. All right, so we're losing basically 1 bit every time we iterate. And then eventually, by here we got, our errors, we're off by 0.02. Here we're off by, basically the magnitude of the answer. So we're, after 26 times through this loop, we're at 2 completely different states. Sensitive dependence on initial conditions. This is it. The initial conditions were the same to begin with, but the precision with which we've represented them is different. The computer's doing its math, but so they're quickly not the same. And once they're not, this action of the sources pushing things away results in them being at different places. Imagine trying to decide what the future state of one of these systems is going to be, if this is the case. Yeah? So in my office, and I'll bring this in at some point, I have this double pendulum. Okay? Maybe you've seen this in some of your classes. It's, a single pendulum's got one arm, and then the second arm sort of can flip through the first, and so it whips around all over the place. If we took good measurements of that thing, its mass, and analyzed it really well, we had a video to measure within, millimeters what its position is to start, and then we let it go, it's going to do some crazy stuff, and best computer in the world, best measurements we could make, probably only be able to say what it's going to do for about 2 or 3 seconds. And it's because of this. This is sometimes called the butterfly effect or sensitive dependence. We're going to characterize it mathematically today. All right, questions about what you're seeing here? All right, so you can have the sort of butterfly effect idea in your head. Just if you saw the Ashton Kutcher movie, you can take that out of your head. Unrelated. Okay, so we're gonna because this is complicated to analyze the difference in how it's growing. Basically, it's growing exponentially, the difference, but it's complicated to analyze by hand. What we're going to do is start with a simpler model than the logistic map, and look at what happens with sensitive dependence for it. And we're going to need some modular arithmetic to start, so many of you will not have seen that. So we'll say that if I have a number and then I'm asking you to represent that number mod 1. So y is just some number, 73.2 or pi, and then I'm going to take its mod 1. This stands for the number y plus n, where n is the unique integer such that 0 is less than or equal to y plus n is less than 1. So the outcome of this mod 1 thing is we're going to end up with a fraction between 0 and 1. We don't really care about what the integer n is, but easier to understand with examples. So if I say 8.23 is the number I care about, and I want to know what it is mod 1, I just subtract the 8 off, and I'm left with 0.23. This is between 0 and 1. So I'm looking for the fractional part. But if it's negative, if it were negative 8.23, then I have to give you what it would take to get to an integer. So that's 0.77. Some of you have seen this before, but it's okay if you haven't. All right, and we're gonna think about a map like the logistic map, but using this type of arithmetic to keep us between 0 and 1. We're going to do, actually, random number generators will work a similar way to what I'm showing you. If you want randomness between 0 and 1, what we're going to do is, do something crazy like the logistic map, but then just keep the integer part of what's left after we square or raise a number to the 5th power or something. So we'll consider the map f of x equals 3x. So I'm going to triple the number x, and I'm going to do it mod 1. So once that output of f gets bigger than 1, I'm going to throw away the integer part, for example, and just keep the fraction that's left. And we're going to do this on the unit interval. Okay, so if I were going to draw a picture of this, here's x, here's 3x mod 1. Always when we do our pictures, we're going to draw, the y equals x line, and I'll have 1 is my bounding box here that I live in. So the function 3x is, normally it's just, this linear function with slope bigger than with slope 3. It's going up and down. But for the purposes of this discussion where we're doing the mod 1 version of it, it just sits inside this little box. And there'll be some slope 3 lines here. Open circle at the top at 1/3. And I should intersect at 1/2 with the next one. So those are all slope 3, trust me. 3 open circles at the top. Intersection with y equals x at 0, fixed point at 0, fixed point at 1/2. Does that make sense? If I plug in 1/2, do I get 1/2 back? Yeah, good. Right, 1/2, plug it in, I get 3/2 because I multiply it by 3. Take off the integer part of 3/2, I get 1/2 back. So I've manufactured that fixed point at 1/2 with this modular business. Not a continuous function. Most of the stuff we look at in the class are continuous, but anytime I do this modular arithmetic, I'm tearing it apart. But this is everything, okay? Because anything to the right of 1, I'm truncating the integer part and bringing it back. Same thing left. All right, so this is interesting. 2 fixed points. You're going to be doing the periodic table for this, by the way. So you're going to, like this thing iterated with itself is going to have 9 vertical lines, 9 slope 9 lines, open circles, 9 open circles, 8 intersections with y equals x. Powers of 3 are going to be a thing on your next attempt there. Okay, so this is what we're going to use to try and understand, just because it'll be easier to triple a number than to multiply it by 4 and then multiply that by 1 minus x. Since it'll be easier to triple a number and something nearby, we'll talk about this sensitive dependence this way. Questions about what's on the board presently? Okay, so we have our modular arithmetic. We're thinking about sensitive dependence. All right. We'll also need another definition. We call a point eventually periodic. There's so many interesting things going on. We're going to need words to be precise about what exactly is happening. We'll call a point eventually periodic with period p. For the map F. If for some positive integer capital N, we have Fn plus p of x, and we want Fn plus p of x, iterating f that many times, to be equal to Fn of x for all n greater than or equal to some capital N. And if p is the smallest such integer. Positive integer. This is a long definition, so we're going to talk about it. But you have seen the basic idea behind this previously. So All right, we're going to call a point P eventually periodic with period P. For the map F, if for some positive integer n, so that's like, I've iterated for a while. This is like, take some transient stuff, do it, and then after some number of iterates, the following is going to be true. That's the capital N part. If I take F little n, and I look at what happens at iterating it then P more times, I get to the same place. So let's see. So what would I want to say about this? Well, I guess we could just start with the fixed point at 0. So you don't see, well, with the fixed point at 0 and the fixed point at, I don't know what the value is here, but the transient behavior would cobweb. These both would cobweb up to that sink. And I can see that here. Cool. However, by hand, if we were doing this, analytically, the green orbit and the red orbit, they never actually get to that point. They just get closer and closer. Because the cobweb, if you think about what it's doing, it's like it's in the limit that the length of those lines is going to 0, but it's never 0 for any integer number of iterates. There's no capital N for which this is true. However, if my initial value was 1, and after one iterate it lands on 0 and stays there forever, then it satisfies this definition. 0 is eventually periodic to the source at, or 1 is eventually periodic to the source at 0. Let's say what these numbers would be. So 1 is eventually periodic with period 1. P would be 1 there. For the map F, if for some positive integer n, which I think would be 2, if we started at 1, then as long as we iterate once, then we're far enough along. F2 is F1, and that's true. There's no smaller p for which that's true. And that's true for all of the n bigger. So F3 is equal to F2, F4 is equal to F3, and so on, because 0 doesn't go anywhere. All right, so there's going to be, this is going to be a little harder to visualize, but we're going to do it anyway. We're going to try. Here we go. Cool. So here I have a period 2 sink. Everything in the interval, aside from 0 and 1, lands on that, is attracted to that sink. And I've said this, but we also have a source at, whatever this value is here. Do you think there are going to be points that map to that source? Could you see, how could you see what those would look like? Where would they be? Yeah. Oh, you mean like that one there? If I draw a horizontal line to y equals x from this spot, it lands at the source. And does it go anywhere after that? So, for example, this x value here, whatever it is, does it go to the square? No, it doesn't. So this point is eventually periodic, just like the example we saw a minute ago. 1 was eventually periodic to 0. This point here is eventually periodic to that source. Cool. Does anything else go to that source? Does anything map to that? I'm going to use the wrong end of my marker. But if I did a vertical line to the function, down to y equals x, this is the backwards thing. Vertical line to y equals x, horizontal line to the function. That point right there iterates, and after 2 iterates, lands on the source. What about every single pre-iterate of that point? There are infinitely many of those, just going back in time. They all, they're getting closer and closer to 0, but all of them are eventually periodic to the fixed point source right here, and not in the basin of this square. Cool. So we're understanding this eventually periodic business, and so the intersection of those two, that was an excellent observation. Very good. And in fact, when this bifurcates to period 4, and that square is still sitting there in between. We just don't see it. So there's a square, right in here. There are going to be points that land on that square. And for points that land on that square, the period will be 2. P will be 2. And so it won't be that F and like F2 and F3 equal each other, and then F3 and F4 equal each other. But rather, it will be, P will be, so it'll be F2 and F4, or F8 and F10 that equal each other. And so it's not periodic, but it's with period 1, but it would be with period 2 there. And for the points that do land on, the points we were just talking about a second ago that land on, like this point right here, that forward iterates to land on that source, and stuff that it came from, there's an infinite sequence of them going backwards in time, closer and closer to 0. They all are eventually periodic to that source. Yeah. What was I going to say about them? Oh, yeah, the n is much longer for them. So there's one really close to 0, for example, for which the n is 10,000. So it takes 10,000 iterates before it lands on the source. Super close to 0. Like so close that we couldn't write it down on the computer. And possibly an irrational number that we couldn't do even if we had any finite length precision. Okay, so lots of points are going to have this property. We actually call it EP instead because it's hard to write these things over and over again. Eventually periodic. We're going to have another thing that's called asymptotically periodic for stuff that approaches and in the limit. So things in a basin of a sink will be asymptotically periodic to the sink. Sinks don't always have things that are eventually periodic to them, but sources often do. Question?
So is there a way to cobweb backwards to get as many points as you can to try and see what's out of your basin of attraction of that period too?
You can totally do that. Because in this case, this function is a quadratic, tail's pointing down. Its inverse is not a function because it's like this way and doesn't pass the vertical line test. But there will always be a pair of options to decide when you go backwards in time where a point came from. And so I think we're not going to be doing a ton of that, but there will be times in the semester where I'm going to ask you to think about what are the inverse images of all of the points that we care about. And we'll do that for, if we wanted to visualize all the sources and points that went to sources, we would need to do something like that. Yeah, and later in the semester when we're talking about fractals, we'll do something like that. Other questions? Okay, so this is a lot of words, but it means, in other words, X maps after a while, potentially, onto a periodic orbit. Could be a source or a sink. In the examples we were just talking about, it was eventually mapping onto a source. Cool. Okay, so let's go back to this example, the 3x mod 1 map. Can somebody tell me a point that is eventually periodic in this case? And maybe the picture might not even be the right place to start, but just looking at 3x might be a place to start. So I know, for example, there's a fixed point at a half. Does anything map to a half? A half maps to a half? Yes. Very good. Anything else? Infinitely many things do. 1/6. What happens when you multiply a sixth by 3? It becomes a half. What about, is there another one other than 1/6? You said a 12th? What happens to a 12th? It goes to a fourth. Let's go with it, though. What happens when you send a fourth through? Multiply it by 3. 3/4. Cool. Then what? 9/4. Take away the integer part. Louder. 1/4. 1/4 goes to 3/4, which goes to 9/4, but we're not allowed to say that because we're living between 0 and 1. We take out the 8/4 of it, And we're left with 1/4 again. So 1/4 is on it's on a period 2 orbit. A quarter is on a period 2 orbit. That's awesome. Let's draw that. So I'm probably going to mess it up, but so we want a square. Oh, what am I doing? Vertical line. Yeah, I knew I was going to mess it up. Let me try again. On your paper, find a quarter and 3/4. So there we go. So at 1/4 and 3/4, you got yourself a period 2 orbit. Sink or source? Period 2 orbit, this one. Why do you think it's going to be a source? You're right. Why do you think it's going to be a source? Remember, the stability of orbits depends on the slope of the intersection of the second, in this case, of the second iterator, or you could multiply together the slopes of each of the 2 points on the original period 2 orbit. What are the slopes of these 2 points? 3. Multiply them together. 9. Also the slope of the 9, slope 9 lines that are F2. Cool. Slope's the same everywhere. Super easy to then talk about stability. In this case, there are 3 here, and if I look at F2, there's going to be 9 lines with slope 9. If I look at F3, there's going to be 27 lines with slope 27. All of them are getting bigger. No sinks. Just like the logistic map had no sinks. Why no sinks? We're just tripling points. So if I miss by a little bit, sensitive dependence is going to say, all right, you're going to grow away from, we haven't even gotten really to the sensitive dependence yet, but that difference you have, whatever it is going to triple every time through. All right, so period 2 orbit. 1/4, 3/4, and you said a 12th. So a 12th as an initial condition is EP to this period 2 orbit. Anything else eventually periodic to this period 2 orbit? Yeah. A 36th. Multiply it by 3, you get a 12th. How did you get a 36th? Divided by 3. Are we going to be able to keep doing that? Yeah, so there'll be an infinite sequence of divided by 3s that take me there. We're thinking about ways to land on a quarter. Can I land on 3/4 in other ways? Nine twelfths. Is that 3/4? Where are these points we're talking about? A 12th, it's over here somewhere. And so what's happening is it's, a 12th comes up and then over and lands at it's the thing that maps to a quarter. And then even closer to 0, there's other points. I'm wondering if there's a way to land on a quarter, land on a third in a different mechanism. Like, is there a spot like between a half and 2/3 that if I evaluate it, takes me up to the function here? Something between a third and 2/3 that is sent to 3/4. Probably something between 1 and 2 if we didn't mod. Did someone say 7/3? 7/12ths? What happens when you multiply 7/12ths by 3? 7/4. Take away 4/4, 3/4. Oh my gosh. 7/12 is also EP to this thing. 7/12 lives between a third and 2/3. Does anything map to 7/12? Probably lots of things, yeah. All right, so this eventually periodic story is going to help us understand, in this case there are no sinks, but sometimes there are going to be sinks, and we're going to want to know what are the boundaries of those sinks. They're going to be points that are EP to sources. Cool. No sinks here. But in the example, that cubic from the first day, there was a whole set of points that were EP to the source at 0. And they were the boundaries of the basins of the two sinks at plus or minus 1 that went to either, the points that went to either. Questions about stuff that's happening? Okay. Let's think bigger. Let's think bigger. I got a lot of numbers between 0 and 1 to think about here. I got this, these two fixed points. I have this square, which is a period 2 orbit. Is it the only period 2 orbit? How many crossings will there be of F2 with y equals x? 9. I'm going to throw that last one away because it's open circle. But yes, 8. Let's say 8, because there's 2 here. So 8. There are 8 crossings of F2. There are going to be 9 lines of slope 9. Of those 8, how many were fixed points of F? The 2 that are up there, leaving 6 behind. So this is one of how many squares? There are 3 squares. So there's 2 other period 2 orbits that aren't on here. We can figure out what they are. We're not going to. You fill out a periodic table about this. There'll be a whole bunch of sources. Question. Are there points between 0 and 1 that don't go and eventually land on one of those sources? I mean, what we've just seen is that if I have like 4 times a power of 3 in the denominator, I'm going to this square. And if I have 7 over 4 times the power of 3 in the denominator, I'm going to go to this square. It's not the only square. There are other squares. And higher period orbits. Cool. Every rational number is eventually periodic to a source. Is that all the points between 0 and 1? No, there's some others. They're the irrational numbers that repeat forever or don't ever repeat as the representation goes out. And no matter how many times we triple them, they're not going to land on one of our sources. However, every rational will. Multiply it by 3 lots and lots of times, and eventually, whatever base you're looking at, whatever stuff is the transient that doesn't have a bar, that stuff is going to disappear. As you multiply it by 3, that gets pushed to the left-hand side of the decimal point and erased by the mod. So you iterate this rational number over and over again. Eventually, you hit the spot where it has the bar of repeating digits because it's rational. And believe it or not, that bar of repeating digits, if we wrote this number in base 3, would have as many ternary digits in it as the length of the periodic orbit that it's on. In base 3, we multiply it by 3, and we just shift the point over, erase the integer. Shift the point over, erase the integer. Nothing else changes. And we're going to end up with every rational number being eventually periodic to a source. This is craziness. This is just a line with slope 3. It's got the mod thing, which is helping the insanity. But so that's interesting, because if you want to measure your initial state and say, what does it do? Does it go on forever doing craziness, or does it settle down onto some repetitive behavior? There's no measurement resolution at which you can answer that question, because you're always going to grab a little interval of measurements, and the rationals in that interval go to a source, and the irrationals bounce around forever, never repeating. Yes.
Statement of every rational number is eventually periodic is or specific to functions dealing with.
There will be other types of functions for which what I said is true. It is going to be true of any function, slope bigger than 1, modular arithmetic. Yeah. I don't expect that you quite understand why right now, but it's just a vision of what you're going to get as we move along. Do you want to? There was a follow-up question.
Just don't assume for other functions.
Yeah, that's right. Yep. So like the logistic map, for example, I can tell you lots of rationals and irrationals that end up approaching this square, because it's everything that isn't EP to that source and 1. Every other point is in the basin of attraction of this square, because there's nothing else it can do. Other questions? OK. So this 3x mod 1 map, 3x mod 1, magnifies small differences between 2 points by a factor of 3 each iterate. So if I start near a third, but not at a third, I'm going somewhere else. If I'm a rational number, I'm landing on some other source of high period, potentially. If I'm an irrational number, I'm going to go around forever. Maybe we should just write that down. All rationals, we'll write it. This is an unsubstantiated claim. All rationals are going to be EP to sources. All right, sensitive dependence, we got to define that. We'll let F be a map. On R, a point x0 has this SDIC property. It's a property of points, not maps. SDIC, and we'll write it down in math and then we'll explain it. If there exists, backward E, there exists a distance d bigger than 0 such that any neighborhood, neighborhoods like that little n sub epsilon, any neighborhood of x0 contains a point which we'll call x, such that if I iterate the two forward under f k times and look at how far apart they are. Got a point x, I got a point x0. They're near each other. I iterate them both forward under the map k times. And I find that their difference is bigger than or equal to d for some non-negative integer k, then I will say that the point x0 has sensitive dependence on initial conditions. Points in the basins of sinks, as I iterate them forward, converge on each other. So if I picked 2 points that, for example, the red and green points here, initially they're not actually very close to each other. But in the limit, they get closer and closer. They do not exhibit sensitive dependence. If I went in the computer and perturbed one of these by a little bit, and then looked, as k goes to infinity, what happens to them? They get closer and closer to these other two. That's not true of 0, by the way. If I look a little bit away from 0, and I ask what happens, well, there's a point right next to 0, no matter how close you get. that ends up going to this square. It's also a point next to 0 no matter how close you get that's eventually periodic to the source. 0, sensitively dependent, right? Because nearby, things leave. In fact, sources are easier to prove this for because fixed point sources because, like fk of 0 is just 0. So this disappears. So to show that 0 is sensitively dependent, you just say, well, how big is the kth iterative of a point nearby? Well, it's going away, so that's going to be big. Because the kth iterative of 0 here doesn't go anywhere. So I'm going to read it again. F's a map on R, like our slope 3 or our logistic map. A point x0 has sensitive dependence on initial conditions if there exists a distance bigger than 0. The distance bigger than 0 is like, well, how far away are they going to be after a while? And you can make that as small as you want. Such that any neighborhood of x0, so I can make my, how close should they be to start, as small as I want. I know your d you gave me. I can make that as small as I want. And no matter how small I make it, no matter how close to 0 I get, there are still points near 0 that leave, get further than d away. Maybe you want to think that d and the epsilon neighborhood should be the same size, but it doesn't really matter. Contains a point, and it's not like if with a source everything leaves, but we just want to have one other point that does this. And so this is a property not just of sources, but of other points as well. Points are going to exhibit this. Under the logistic map, when the parameter is bigger, any small perturbation of the red orbit by any small amount means it's going to eventually, it doesn't matter how big your epsilon is, no matter how close you get to it. If I take the green one and I slide it as close as you want, eventually there'll be a distance d away, and you can pick your d. It can be it can't be bigger than, I guess, a half or something for this map because you can't get too far away, but you'll get far away quickly. Or 1. They can't get more than 1 away from each other. Questions about that? The SDIC thing. Yeah.
So, isn't it possible though for 2 points really close together, even so if one is sensitively dependent, they'll go away from each other and eventually they might get back close together?
They will, yeah. Like in this case, the green one and the red one, if the parameter's value is 4, they'll actually get as close to each other as you want eventually. Because this thing's getting mixed together and eventually, you got a room full of particles and you're stirring it up forever, eventually 2 of them are going to come as close as you want.
You just have to know at some point they get.
That's right. Yeah. Right. Totally. Yeah. So this is the idea of predicting the future state of something. And if I guess that it's going to snow a year from today, it might snow a year from today, but I'm guessing. It's really like, all right, so over the short period of time that these are close to each other, they're leaving each other. It's okay if they diverge and accidentally come back. That's not a good prediction.
You're just saying they're not, no distance apart. They're like that point.
Yeah. It's that initial growth that matters.
Right.
The fact that they are constrained by physics to come back near each other, that's not relevant to this, like they spread away to begin with. Yeah.
The main reason we look at it is because they're not the same value. Like there's some point where they, for some reason, they start to go away.
That's right. Yeah. Yep. Other questions? There'll be some return time on average for different stretchings that points will come back together, but here we're just initially thinking about that initial growth. Okay, so there's a table in your book that has an example printout for this. Table 1.4. That's what it's saying. Do I have that? Here we go. All right, so here's the slope. The slope or the slope 3/10 map for that, a quarter, 3/4. And it doesn't matter what precision you use. If you perturb one of them by 10 to the minus 4, the difference grows by a factor of 3 each time, right? That 10 to the minus 4 that's present here that isn't here, that's getting hit by the 3 also. And so, you got close to a quarter, but now that 1 has been multiplied by 3 a couple times, and then it's 27, then it's 81, and then it's 243, and it's growing. And then eventually, by the 10th iterate, they're totally different. So yeah, maybe like this orbit right here will eventually get as close to either of these as you want, but that's like 1,000 from now. Sensitive dependence. Questions? Okay, we got a couple minutes left. One last concept for the weekend. It's not the actual weekend yet, it's the chaos weekend, starting in 5 minutes. Cool. So itineraries. There's a lot of digits required to analyze the orbits of these points. And we're going to abstract away a little bit from doing that. And we're going to consider, so here's my logistic map, 4x1 minus x, capital G. So we know that the dynamics here are complicated. We've seen that. However, we can analyze it. What we'll do is we'll divide the interval from 0 to 1 into just the two halves. Am I smaller than a half? Call it L. Am I bigger than a half? Call it R. Left and right. And then to analyze an orbit and what it does, what an initial condition does, we're going to write down a string of L's and R's that tell us where am I each iterate through. So for example, if I start with this fixed point right here as my initial value, 3/4, x1 equals 3/4, and I send it through the map, what do I get for x2? What happens when I send 3/4 through the logistic map? I get 3/4 back. And that stays forever because it's fixed. However, in this view, I start in R and I stay in R forever. So the orbit, instead of writing down a bunch of 3/4, what I'm going to write down is R with a bar over it. What do you think the orbit for 0 is going to be? What the itinerary will be for the fixed point 0. It'll be L bar. And what we're going to find is that we can often, at least for the logistic map, this is true, for 4 this is true, we're going to have a unique string of L's and R's for every point. For this logistic map, that's true. Be easier to see, let me see, well maybe I'll pick another point. So this point right here that I'll draw in red, there's an x1 that if I evaluate it, I get a number back that's also in L. So that x1 started in L, and then I'm going to put L again after it because it stayed in L. But when I iterate it again, I think I'm going to end up with something in R. That point, if I look on the y-axis, is in R. You got to kind of decide, am I going to look at the x-axis to read off the L's and R's or the y-axis? Does not matter which one you do, you just got to stay there. Stay consistently on one of those two axes for writing down these letters. So x1, x2, I started in L, I stayed in L, then I went to R. Horizontal line to y equals x, down to my function. I am back in, I've been reading off this axis, yeah? So now I'm back in L. This is a small number. LLRL. Okay, headed over here. Still in L after I iterate again. Landed in R on the second trip through. Still in R. All right, so you can see what's going on here. That point, I don't know what's going to happen, but instead of writing down its digits, which is a mess to do by hand, computer's great at it, we can write down these letters, which are effectively, if we write the orbit point, x1, in base 2 in binary, is the first bit a 0 or a 1. That's telling me if I'm on the left or right half of the interval from 0 to 1. If I'm smaller than a half, the first bit is going to be a 0. If I'm bigger than a half, the first bit's a 1. This is a way of encoding the location information. It's very lossy as an encoding because I'm throwing away all the other stuff where I am except am I on the left or right half. But it'll give me a really powerful way to symbolically, this is called symbolic dynamics, symbolically analyze the orbits of these points. It's like an address, like a IP address for a point or on a map. So we've done this now for an example, a few examples for that logistic map. Remember the one we looked at the first day of class was a half x, or the parameter, sorry, not a half. This function was little g, 2x, 1 minus x. Different story here. In this picture, am I allowed to map to points between 1/2 and 1? Like, does the function ever return a value above a half? Some of you are worried about what happens. What do we call a half if it's on the boundary? Don't worry about it now. Either L or R will be fine. Just stay consistent. Okay, I got a fixed point here. I got a fixed point here. Let's call that fixed point as being an R just to distinguish it from this one over here. So 0 is L bar. It doesn't go anywhere. That's the orbit of 0. What's the itinerary of 1? What would, if I initialize with 1, is 1 an L or R? It's an R. And then where does it go? It goes to L, and what happens? It stays. So I got an R, and then I got an L bar. Are there other itineraries than the ones I wrote down? I see some nodding. What if I started just to the left of 1? What would it do? 0.9. That's in R. Where does it go? It's in, sorry, 0.1, or it's 0.9. This is, let's say it's right here. It goes over here to y equals x, up, over. Got a lot of L's. Do I ever get an R again? No. So 0.9, also RL bar. That's kind of annoying. Every other point, aside from this fixed point, that's on the right half will have the itinerary RL bar. Every point on the left half that starts in the left half will have the itinerary L bar. And there's no other things happening. Sinks will result in typically kind of boring itineraries where all the points in the basin, they kind of do the same thing. But if it's period 2, if I got a period 2 orbit, that's over here somewhere, right? Isn't there a period 2 source in here? Like, let's say it's this one. It's totally time to go. Period 2 source. What do we think the period 2 source is going to be? Its itinerary. In that case, it's actually my square is too small. It ends up being something like this. Yeah. So the period 2 source is going to have an itinerary LR bar or RL bar. Those will be the itineraries of the 2 points. Very cool things happening. Yes?
The bar go over both the L and the R?
Yes, it would. Okay, that's enough for today. Have a great weekend.